All right, in this video, I want to take a quick look at how symmetry can help us with certain integrals. And the example we're going to look at asks us to calculate the integral from -1 to 1 of tangent x over the quantity 1 plus x squared plus x to the fourth dx. Now, for this one, the integrand is quite complicated. We've got tangent of x in the numerator, and we've got 1 plus x squared plus x to the fourth in the denominator. That is a little bit more complicated than anything we've seen before. And I don't know any functions like this that we can easily antidifferentiate. But I can tell you that this is equal to 0. And a very simple way to do this is by looking at the function and recognizing that this is an odd function. And because it's an odd function and we're integrating from -1 to 1, the positive area on one side is going to be equal to the negative area on the other side, and they're going to end up canceling each other out. We actually have two rules that we can use when we're looking at integrals that involve symmetry. And I'll give you those rules now. So in each of these examples, suppose f is a continuous function on the closed interval from -a to a. If f is an odd function, which is what we saw up here, then the integral from -a to a of f of x dx is equal to 0. And I can show you a quick sketch of why that's the case. If we have an odd function, then there is rotational symmetry about the x-axis. So if this is part of the graph, then we know on the other side, the graph is going to look something like that. It's not a perfect drawing, but you get what I mean. And if we're taking the integral, which is looking at the area under that curve, then any positive area we're going to get on one side is going to be canceled out by negative area on the other side, right? And it's not necessarily going to mean one side is positive and the other side is negative. It might be that one side has positive and negative bits, but then the other side has negative and positive bits, and the negative bits on one side cancel out the positive on the other, and the positive bits on one side cancel out the negative bits on the other. Anyways, I think you get what I mean. Basically, the two sides are going to be opposite, and so they cancel. Now, if f is even, we don't have as nice of a rule, but we do have something that's a little bit helpful. If it's an even function, which means it's symmetric across the y-axis, then if we want the integral from -a to a of f of x dx, what we can do is we can double the integral from 0 to a of f of x dx. Let me again give you a quick diagram so you can see why this might be helpful and why it might be true. If we have an even function, then that means whatever it looks like on one side, we've got a mirror image on the other. And so if we are looking to integrate this from -a to a, whatever we have on one side for our area, whether it's positive or negative, it's not going to cancel out with the other side, but they will end up being equal to each other. And so what that means is instead of integrating from -a to +a, we can just take the integral from 0 to a, and whatever we get, we can double it. Now, why is that helpful? Well, if we're using the fundamental theorem of calculus to integrate, then we're going to find the antiderivative and evaluate it at a and 0, and that's nicer than evaluating it at a and -a. Usually, plugging in 0 to a function is a lot simpler. There's a lot more cancellation than other things. So this just makes the calculation at the end of the day a little bit easier. We can look at an example. If we wanted to integrate, let's say from -3 to 3, the function x to the fourth dx, we could find the antiderivative and plug in 3 and -3 and all of that. But instead, what we're going to do is we're going to write this as 2 times the integral from 0 to 3 of x to the 4th dx. This is an even function. And then we know the antiderivative of x to the 4th is x to the 5th over 5. We can evaluate that at 0 and 3, and we know when we evaluate this at 0, it's going to be 0, which is much nicer than trying to plug in -3. So anyways, we've got 2 times 3 to the 5th over 5 minus 0 to the 5th over 5. And that second term is 0. Life is good. Now 3 to the 5th, 3, 9, 27, 81, 243 over 5. And that's going to end up being 486 over 5. It's just a little bit nicer than having to plug in 3 and -3. Saves you just a little bit of calculation.